So today we will see the topic sequential circuit of the second unit. So now already I have told you that there are two types of circuits in digital electronics. One is combinational circuit and another one is sequential circuit. The combinational circuit consists of only logic gates and the output depends only on the present input, and it will perform any operation that can be specified by set of Boolean function. Now we come to sequential circuit. The sequential circuit will be having combinational circuit plus storage elements. The storage elements may be flip-flop or latch. So here in the sequential circuit, the output is a function of both the function of input and the state of storage elements. That is, the output depends upon the present input and the past input. Okay, but in the case of combinational circuit, output depends only on the present input. But in the case of sequential circuit, the output depends on the present input and past input. And in sequential circuit, it will be having combinational circuit plus memory elements. Now, in sequential circuit, there are two types. One is synchronous sequential circuit and the next one is the asynchronous sequential circuit. In synchronous sequential circuit, the circuit can modify their state only when a clock pulse is applied. So in synchronous sequential circuit can modify its state when a clock pulse is applied. But in the case of asynchronous sequential circuit, it can modify their state at any time. So here the synchronous sequential circuit can change the state only when there is clock, but in the case of asynchronous sequential circuit, it can modify its state at any time. So in asynchronous sequential circuit, feedback from memory can cause instability. So asynchronous sequential circuit is unstable and it is much less used. Now in synchronous sequential circuit is also called as clocked sequential circuit. In the synchronous sequential circuit, there are two types. First one is Moore model and the second one is Mealy model. So there are two types in synchronous sequential circuits. One is Moore model and the second one is Mealy model. In Moore model, output is a function of present state only. That is nothing but it depends only on the output of the flip-flop. But the Mealy model, output is a function of external input and present state. So in synchronous sequential circuit, there are two types of circuit. One is Moore model and another one is Mealy model. In Moore model, the output is a function of present state only, and Mealy model is Mealy model output is a function of input and present state. So once again, the sequential circuit can be classified depending on the timing signal. There are two types: synchronous sequential circuit and asynchronous sequential circuit. In synchronous sequential circuit, the signal can affect the memory elements only at discrete instance of time. Discrete instance of time means whenever you are applying clock, the output can change. Okay. In synchronous sequential circuit, the signal can affect the memory elements only at a discrete instant of time. But in the case of asynchronous sequential circuit, the signal can affect the memory elements at any instant of time. So this is a major difference between synchronous sequential circuit and asynchronous sequential circuit. Now, in the feedback path, the memory elements will be flip-flop and latches. These are bistable elements. The flip-flop and the latches are called bistable elements. Bistable elements means it will be having two stable states, that is logic 0 and logic 1. And it is namely Q and Q bar. The outputs are complementary. These flip-flop and latches are bistable elements and it is having two stable states, logic 0 and logic 1, and it is named as Q and Q bar, and the outputs are complementary. The meaning is when Q is equal to 0, Q bar will be 1, and when Q is 1, Q bar will be 0. Next one is latch. What is latch? Latch is a sequential device that checks all of its input continuously and changes its output accordingly at any time independent of the clocking signal. So latch is nothing but it is a sequential circuit or sequential device. It checks the input continuously. Continuously, it will be checking the input and changes its output accordingly at any time, independent of this clocking signal. In latch, there is no clocking signal, and it output can change at any time. So in the latch, a 1-bit information stored is latched. Therefore, the circuit is referred as latch. Why it is called latch means in the latch, the one bit information stored in the circuit is latched. So it is called a latch. Now we are coming for flip-flop. Flip-flop is also a sequential device that normally samples the input and changes its output only at the times determined by clock signal. So the flip-flop will change the state with respect to the clock signal, and this latch will change its state at any time independent of clock signal. In simple, we can say that flip-flop is a 1-bit storage element. Now, what is the difference between Moore model and Mealy model? In Moore model, output is a function of present state only, and in Mealy model, output is a function of input and present state. So when you are coming for the state diagram, so actually state diagram is nothing but the pictorial representation of a behavior of a sequential circuit. Okay, the state diagram is nothing but the pictorial representation of behavior of a uh, sequential circuit. So in that state diagram, in Moore model, output is written inside the circle. So in the state diagram, states are represented by circle, and transition between the states are represented by a line segment with the arrowhead. So the output is written inside the circle in Moore model, and in Mealy model, the output is written in transition edge in the state diagram. So there are two difference. First difference is in means of output. In output, uh, output is a function of present state only in Moore model, and in Mealy model, output is a function of input and present state. When coming to the state diagram, in Moore model, we will be writing the output inside the circle, and in the case of Mealy, we will be writing the output in the transition edge. Next one is this is the Moore model's state diagram. So here we are writing the output inside the circle. Okay. Now we are coming to the Mealy model. In Mealy model, we are writing the output in the transition. Above the line segment, you will be writing the output. So this is the state diagram of Mealy model. Now we'll see the Mealy circuit and Moore circuit. So this is a block diagram of Mealy circuit. This is the output circuit. This output is depends upon both input as well as the present state. This is the output of the state register is nothing but the present state. So the output is depends upon both input as well as both input. This is the external input as well as the output of the register. Now next one is the Moore circuit. In Moore circuit, output depends only on the present state, and it is independent of the external input. Next, we will see the what are the difference between combinational circuit and sequential circuit. So in combinational circuit, output variables are at all times depend on the combination of input variables. But in the case of sequential circuit, output variables depend. But in sequential circuit, output variables depend not only on the present input variables, but they also depend on the past history of these input variables. Then next difference is memory unit is not required in combinational circuit, and in sequential circuit, memory unit is required to store the past history of input variables in the sequential circuit. Then combinational circuits are faster in speed, but sequential circuits are slower than the combinational circuit. Combinational circuits are easy to design. Sequential circuits are comparatively harder to design. Parallel adder is a combinational circuit. Serial adder is a sequential circuit. This is an example of combinational and sequential circuit. Next, we are going for NOR gate. So, this is a truth table of NOR gate. So, from this truth table, we understand that in a NOR gate, if any of the any of the one input is 1, then the output is 0, and the output is 1 if both the inputs are 0. So, if any one of the input is 1, the output becomes 0. The first point is if any one of the input is 1, output is 0, and if any one of the input is 0, output is a complement of other input. Okay, so if any one of the input is 0, if any one of the input is 0, output is a complement of other input. If any one of the input is 0, output is a complement of other input. Okay, so these two things we understand from the NOR gate. Now we are going for basic. We are going for basic NOR SR latch. Okay, we are going for basic NOR SR latch. So this is the circuit diagram of basic NOR SR latch. Here you are having two inputs, set and reset. So these two are NOR gates. The output of this NOR gate is connected to the input of this NOR gate, and the output of this NOR gate is connected to the input of this NOR gate. This is cross coupled NOR gates. So it is having two inputs, set and reset. It is having two outputs, Q and Q bar. So it is having two inputs, set and reset, and it is having two outputs, Q and Q bar. So these outputs are complement of each other. So these two outputs are complement of each other. So the cross coupling of these two NOR gates gives the SR latch. So we got the SR latch by cross coupling these two NOR gates. Now this is the truth table of your basic NOR SR latch. So you are having two inputs, S and R. So we know that if you are having two inputs, it can have four combination. That is 0, 0, 0, 1, 1, 0, 1, 1. These are the four input combinations. Okay. Now, when your S is 0 and R is 1, the output of your SR latch is 1. So it is if S is 1 and R is 0, the output Q is nothing but 1. Okay. Similarly, when S is 0 and R is 1, when S is 0 and R is 1, your Q will be 0. Okay, first condition okay. Second condition, first condition is when S is 1 and R is 0, your Q is 1. Second one, your S is 0 and R is 1. First condition, S is 1 and R is 0, output is 1. And the second condition, S is 0 and R is 1, your output will be 0. Then both the inputs are 0. When both the inputs are 0, you will get Q as 1 if you are getting the 0, 0 after S is equal to 1 and R is equal to 0. If the 0, 0 is coming after this state, you will be getting this Q as 1. Similarly, you will be getting S as 0 if this is coming after S is equal to 0 and R is equal to 1. So, in an SR latch, 1 input we can't give. It is a forbidden one. You have to put down case. It is forbidden. So you can't. So in SR latch, the input one is a forbidden one, and it is we will put as X. We will not give the input 1 1. Okay. Now we are going for to check the working of this NOR latch. So we are considering S is equal to 1 and R is equal to 0. Okay, S is equal to 1 and R is equal to 0. So we have already studied that from the truth table of the NOR gate. One of the input is 1, output is 0. Okay, so we have already studied that if one of the input is 1, so first we are going to check the first condition, S is equal to 1 and R is equal to 0. Okay, now giving S is equal to 1 and R is equal to 0. And from the truth table of NOR gate, we know that if one of the input of the NOR gate is 1, its output is 0. If this output is 0, if Q bar is 0, Q is 1. So these two are complement of each other. So we got the first output, that is when S is equal to 0, sorry, when S is equal to 1 and R is equal to 0, we got Q as 1. Okay, when S is equal to 0 and R is equal to 0, we got Q as 1. Next, we are going for S is equal to 0 and R is equal to 1. So we are putting S is equal to 0 and R is equal to 1. So we know that if one of the input to an OR gate is 1, its output will be 0. If Q is 0, Q bar is 1. So we are getting when S is equal to 0 and R is equal to 1, Q is equal to 0. Okay. Next we are going for S is equal to 0, R is equal to 0 and Q as 1. Okay. Q we are taking as 1, S is equal to 0 and R is equal to 0. Now this 1, it is coming as feedback to this NOR gate. We know that if one of the input of this NOR gate is 1, then its output is 0. If Q bar is 0, then Q is 1. So when S is equal to 0, R is equal to 0 and Q is equal to 0, sorry, Q is equal to 1, after giving this input, you will be getting Q as 1 in the next state. So this Q is equal to 1. Initially what you have taken is nothing but the present state, and this Q what you are getting is nothing but the next state. So when you are having S is equal to 0, R is equal to 0 and Q is equal to 0, again you will be getting this Q as 1. Okay. So when your S is equal to 0, R is equal to 0 and Q is equal to 1, again we will be getting this Q as 1. I already told you that this one will be coming as a feedback here. So one of the input is 1, here we will be getting 0. So automatically the complement of this one you will be getting here. Okay. Next one, S is equal to 0, R is equal to 0 and Q is equal to 0. Okay. Now both S and R are 0 and you are taking Q as 0 here. If Q is 0, this Q bar is 1 at that time. Q bar is 1. This 1 is taken as feedback at this point. So if one of the input of an OR gate is 0, then the output will be 0. So when you are considering S is equal to 0, sorry, R is equal to 0, S is equal to 0 and Q is equal to 0, again you will be getting Q is equal to 0. Then we are going for, this is nothing but what initially what you seen is a basic SR latch. Now we are going for gated SR latch. This latch is made up of NAND gates. So this is the gated or enable or clock signal. So in the gated SR latch, you have given one control. That control is nothing called clock or enable or gated. Okay. So whenever the C is 1, then only the circuit will work. If you give this as 0, the circuit will not work. Okay. Now this is the gated SR latch using NAND gates. Okay. Here you are having two cross coupled NAND gates, and these are the inputs. S and R are the inputs. So here you are having Q and here you are having Q bar. So now first I already told you that you are having, if you are having two inputs, you'll be having two combinations. Okay. Now before going to this explanation, I will tell what is meant by present state and what is meant by next state. Present state is nothing but before providing the input, what is present in the output of the flip flop, it is nothing called present state. So after providing input, what you are getting as the output, it is nothing called the next state. So whether it is a latch or flip flop, whatever it is present in the output before the application of input and clock, it is called present state. And whatever you are getting after application of input and clock is called next state. Okay. So I am taking two inputs S and R, and I am taking the present state as Q and next state as present state as Qn and next state as Q of n plus 1. I am taking, and first I am taking present state as 0. First I am considering this 0, 0, and this as 0. So I am taking S as 0, and I am taking S as 0, R as 0, present state as 0, present state as 0, and I am considering clock as 1. So in an AND gate, if any one of the input is 0, then the output is 1. So here also one of the input is 0, so output is 1. Okay. Now here you are having 0 and here you are having 1. Now this 1, it will be coming as feedback to this NAND gate. In an AND gate, if both the inputs are 1, then the output will be 0. So the next state you are getting 0. When you are giving S is equal to 0, R is equal to 0, C is equal to 1, and Qn is equal to 0, in the next state you are getting Q of n plus 1 as 0. Next I am taking S is equal to 0, R is equal to 0, C is equal to 1, and Q of n is equal to S is equal to 0, R is equal to 0, Qn is equal to 1. Okay. I have to find out what is Q of n plus 1. Now here one of the input of this NAND gate is 0, automatically output is 1. Here also one of the input is 0, automatically the output is 1. So here you are having 1. So this 1 is fed as input to this NAND gate. In an NAND gate, if both the inputs are 1, automatically output will be 0. So if Q bar is 0, then Q is 1. So if S is equal to 0, R is equal to 0, and Qn is 1, Q of n plus 1 is 1. Okay. Next we are taking S is equal to 1, R is equal to 0, and Q of n as 0. If Q of n is 0, then Q bar will be 1. So if one of the C is 1. So if both the inputs are 1, then the output of the NAND gate is 0. If one of the input um, if one of the input is 0, then the output will be 1. Okay. Now So you are having QS or QN as 0. So here you will be having 1. So you have to consider this 1. This 1 will be feedback to this NAND gate. So in NAND gate, if one of the input is 0, then the output will become 1. So when S is equal to 1, R is equal to 0, and Q1 is equal to 0, your Q of n plus 1 is 1. Next we are considering S is equal to 1, R is equal to 0, and C is equal to 0. So if both the inputs are 1, the output is 0. Here one of the input is 0, so output is 1. Okay. Now here you are having 1. Q as 1. So this 1 will be feedback to this NAND gate. If both the inputs are 1, the output is 0. So if Q bar is 0, Q is 1. So when S is equal to 1, R is equal to 0, and Qn is 1, Q of n plus 1 is 1. Okay. So whenever you are considering this feedback, you have to consider the ones. So next we are considering S is equal to 0, C is equal to 1, and R is equal to 1. So here one of the input is 0, so output is 1. Here both the inputs are 1, so output is 0. So since you are having 0 here, here you will be having 1. This 1 is feedback to this NAND gate. If both the inputs of an NAND gate is 1, its output is 0. So when S is equal to 0, R is equal to 1, and Qn is equal to 0, in Q of n plus 1, you will be getting 0. Next we are considering S is equal to 0, C is equal to 1, and R is equal to 1. So here one of the input is 0, so output is 1. Here both the inputs are 1, so output is 0. And here the value of Q is 1. So this 1 will be feedback to this NAND gate. So one of the input of this NAND gate is 0, the output is 1. So here you will be getting 0. So when S is equal to 0, C is equal to 1, and R is equal to 1, and when Qn is 1, Q of n plus 1 you will be getting as 0. And in SR latch, the S is equal to 1 and R is equal to 1 is a forbidden state. We should not give the input S is equal to 1 and R is equal to 1, and it is called as a forbidden state. So this is the truth table of the SR latch or SR flip-flop. This is the enable or clock. When clock is 0, whatever you are giving in the input and whatever may be the present state, the present state will be coming in the next state. No change will be there. So in when you are providing no clock and whatever may be the inputs, what is present in the present state, that will be getting in the next state. Now you come to when you are making enable as 1. We are making enable as 1, and first we are considering the input as 0 0. When the inputs are 0 0, whatever you are present in the present state you will be getting in the next state. So first you are considering present state as 0, next we are considering present state as 1. So when in clock is 1 and when S and R are 0, whatever we are having in the present state, it will be coming in the next state. That is no change. Similarly, when your clock is 0, no change. Then when clock is 1 and when S is 0 and R is 1, whatever you are having in the present state, next state will be 0. It is called reset. Similarly, when clock is 1 and S is 1 and R is 0, whatever you will be having in the present state, next state will be 1. And when clock is 1 and when S and 1 are 1, it is indeterminate. This is forbidden state. We are not allowed to. So this is a truth table of our SR latch or SR flip flop fitted SR latch with the clock. Okay, when you're not providing any clock, there is no change in the present state and next state. Similarly, when you are providing clock as 1 and S and R are 0, whatever you are having in the present state, you'll be having in the next state. Similarly, when clock is 1 and when S is 0 and R is 1, whatever you are having in the present state, the next state will be 0. When clock is 0 and S is equal to 1 and R is equal to 0, whatever you are having in the, whatever means either 0 or 1, your next state will be 1. And when clock is 1 and S and R are 1 is a forbidden state. Now, this is a truth table without clock, and this truth table we will be using to find the characteristic equation. Similarly, we will be using it for excitation table. In order to find the excitation table and the characteristic equation, we will be using this truth table. This truth table is also similar to the previous one. When S and R are 0, whatever you are having in the present state may be 0 or 1. The same present state will be coming in the next state. When S is equal to 0 and R is equal to 1, whatever you are having in the present state, the next state is 0. The when S is 1 and R is equal to 0, whatever you are having in the present state, the next state will be 1. When S is 1 and R is 0, whatever you will be having in the present state, it is an indeterminate state or forbidden state. This present state may be 0 or 1, that we doesn't know. So only we are taking it as first we are considering it as 0, then we are considering it as 1. So both combinations we are taking because we don't know what is present previously. Okay. Now we are going for the transition diagram. So this is the state Q is equal to 0, and this is when Q is equal to 1. So when S is 0, 0 and S is 0, 1, it will be, and when Q is 0, it will present in the same state. Okay, it will present only in the same state. Similarly, when Q is 1 and S is 0, 0 and S is 1, 0, it will be in the state 1. Similarly, when you are having S is equal to 1, R is equal to 0 and Q is equal to 0, it will be going to the state Q is equal to 1. Similarly, when S is equal to 0 and R is equal to 1, and when it is in state 1, it will be going to state 0. This transition diagram is nothing but by using the truth table, we can draw the transition diagram. Very simple. First 0, 0, this present state and the next state. 0, 0, 0 means 0, 0, 0, 1 means 1. Then first I will explain this one. So you are in 0, 0, your input is 0, 0, and when Q is 0, the Q of n plus will be 0. So it will be in the same state. So we are written here. Similarly, you are in 0, 0, when S is equal to 0 and R is equal to 0 and you are in state 1. So here S is equal to 0, R is equal to 0 and you are in state 1. The next state is also 1. So it will be present here also, here only. Okay. Now next S, R, Q, Q of n plus 1. Now we are considering S is equal to 0, R is equal to 1, Q of n 0, Q of n plus 1 also 0. S is equal to 0, R is equal to 1, Q of n 1, next state also 0. Now please listen. We are considering S is equal to 0 and R is equal to 1. S is equal to 0 and R is equal to 1. And the value of Q of n is 0. Value of Q of n is 0. So next state is also 0. So it is in the same. So we are considered here. Next S is equal to 0, R is equal to 1. S is equal to 0, R is equal to 1, and you are in state 1. You are in state 1. S is equal to 0, R is equal to 1. So where it is going? It is going to state 0. So this one, it is going to state 0. Similarly, S, R, Q of n plus 1. S1, R0, present state 0. You will be having 1. S1, R0, present state 1, 1. Now you are considering 1 0 and present state 0. You are considering input 1 0 and the present state 0. So when you are having S and 1 as S1 and R0 and present state 0, it is going to 1. So we have put the arrow to 1. Next S is 1, R is equal to 0. S is 1, R is equal to 0. It is in state 1. It is in the same state. So it is present in the same state. Okay, so this is nothing but the transition diagram. One input you can't give to this SR flip flop. Now characteristic equation. So from this you consider this two table. You consider S, R, and Q of n as the input variables, and you take Q of n plus 1 as the output variable. So you consider from this two table, you consider S, R, and Q of n as the input variable, and you consider Q of n plus 1 as the output variable. And by looking the column of this Q of n plus 1, you are having 1 in 0 0 1, and you are having 1 in 1 0 0, you are having 1 in 1 0 1, you are having X in 1 1 0, you are having X in 1 1 1. So first you have to check the column of 1, sorry, Q of n plus 1, and you have to find wherever you are having 1. So how many input variables you are having? 3 input variables. So you have to draw a, so from the two table, we are having 3 input variables. So we are drawing a 3 variable K map, and the variables are input variables of S, R, and Q of n. From the column of Q of n plus 1, this K map is for Q of n plus 1. So we have plotted the ones and don't cares, and we are going for grouping. These are the two groups we are getting. The expression for this group is S, and the expression for this group is R bar Q of n. So this is the characteristic equation of the SR latch or SR flip flop. So this characteristic equation is very important for doing the analysis problems of this sequential circuit. So you have to study this characteristic equation. Q of n plus 1 is equal to S plus R dash Qn. So next we have to find the excitation table. So actually your excitation table will be having 4 columns, that is Q of n, Q of n plus 1, then inputs of the flip flop. Here the inputs of the flip flops are S and R. So for the first combination 0 0 0 1 1 0 1 1. Okay, these are the 4 possibilities of present state and next state. So from the truth table, first we have to check in which are the places we are having present state and next state as 0. So this is a truth table of our SR flip flop. So from the SR flip flop, so we have to check which are the places we are having present state and next state as 0. So we are having present state and next state 0 in 2 places. So we have considered 2 places. So then we have to check in both the places what is the value of S. In both the places the value of S is 0, that is in green. So the value of R is 0 in one place and 1 in one place. So we have to put X. So this is the first one. So first, in order to find that excitation table, first you have to write q of n and q of n plus 1, and you have to write the 4 combinations of q of n plus n and n plus 1, that is 0 0 0 1 1 0 and 1 1. Then you have to write the input of the flip flop having two inputs S and R. Then you have to check the truth table of the SR flip flop in which are places of this having the present state and next state as 0 0 0 0. So from here you are having in two places you are having 0 0. So in both the places the value of S is 0, so you write 0 here, but the value of R is 0 in one place and in R in another place, so you have to put X. Now, so in the excitation table we have written the first digit. Next we are going for the second one. So second thing of our excitation table is 0 1. Now in the truth table we have to check in which place we are having 0 1. We are having 0 1 in only one place. In that place the value of S is 1 and R is 0. So we have entered the value S is 1 and R is 0. Next one is 1 0. Qn is 1 and Q of n plus 1 is 0. So we are checking the truth table in which place we are having 1 0. So only one place we are having 1 0. In that the value of S is 0 and R is 1. Then we are going for 1 1. The 1 1 you are having in two places, that is in one place the value of S is 0 and R is 0. In another place is value of S is 1 and R is 0. So in the table you have to write it as S is equal to X, because in one place it is 0 and another place it is 1. Similarly the value of R is same in both the places, so we are putting 0. Now we are combining this and we are writing the actual excitation table. This is an actual excitation table. Here it will be having 0 0 0 0 for 0 0 0 x, for 0 1 1 0, for 1 0 0 1 1 1 x1. I have told you how to find this. Okay. Now next one is gated D latch. So this SR flip flop is having one disadvantages, that is we can't give both the inputs as 1. So in order to overcome this we are going for gated D latch. In gated D latch what we are doing is we are modifying the SR latch. So we are connecting, or in between S and R we are providing one inverter. So due to this inverter, at a time both the inputs will not be same. So gated latch is nothing but it is a modification. D latch is nothing but another name is delayed latch. Okay. So between S and R of your SR latch, gated SR latch, you are providing one inverter. So at that time both the inputs are not one. Now we are going for the truth table. Here it is having only one input D. Okay. Our gated latch is having only one input. So one input means two combination. 2 to the power 1 is two combination. So this two combinations can have a present state value as 0 and 1. This 0 is a one combination and 1 is another combination. But the 0 can have a present state value of 0 as well as 1. Similarly, this 1 can have a present state value of 1, 0 and 1. In D flip flop or D latch, what you have to remember is the value of D will be copied to Q of n plus 1. Whatever you are having in the D input, that will be copied to Q of n plus 1 irrespective of present state Q of n. So while drawing the truth table, so you have to remember that whatever you are having in that D, it will be copied to Q of n plus 1. So how to draw the truth table? You are having only one input D, that is one input can have two combinations. First 0, the 0 can have the present state as 0 and present state as 1. Similarly, 1 can have a present state of 1 and present state of 0. So you have to copy this D output to the Q of n plus 1. So for all the other things, here it is 0. I will tell how to write the truth table. So we are having only one input, so it can have two combinations. First combination is 0. The 0 can have a present state of 0, as well as 0 can have a present state of 1. Similarly, next is 1. 1 can have a present state of 0. Similarly, 1 can have a present state of 1. So in D flip flop, whatever you are having in the D input, it will be transferred to the next state. So 1 1, it will be transferred to the next state. So this is nothing but how to draw the truth table. So similar to the operation of SR flip flop, also here will be getting this outputs. Now this is the diagram, circuit diagram or logic diagram of D flip flop using NAND gate, and this is the logic symbol, and this is nothing but SR flip flop converter to D flip flop. We have introduced a inverter between S and R. Next is truth table. Already we have studied the truth table. Now this is the transition diagram. So this is the transition diagram. So when Q is 0 and D is 0, it will be in the present state, that is Q is 0. When D is 1 and Q is 0, it will be going to the next state. Similarly, when D is 1 and Q is 1, it will be in the same state, Q is 1. And when D is 0 and Q is 1, it will go to the state Q is equal to 0. So this is a transition diagram. So next, from the truth table, we are going for characteristic equation. So your truth table will be having this is a K-map for Q of n plus 1. So the input variables are D and Q of n. So we are having only two variables by looking the column of Q of n plus 1. So finding the characteristic equation, we are going to draw K-map for Q of n plus 1. And the input variables are D and Q of n. So we are drawing a two variable K map, and we are checking the column of Q of n plus 1. For 1 0 and 1 1, we are having 1. And now we have plotted the values in this K map, and we are grouping, and we are the expression is nothing but D. That is Q of n plus 1 is equal to D. So this is the expression of the characteristic equation of D flip flop. For D flip flop, the next state is nothing but equal to D. So next we are going for the excitation table. Similar to the excitation table ISR flip flop, here also first of all you have to write 0 0 0 1 1 0 and 1 1, and you have to check the truth table for which condition you are getting present state and next state as 0. So D is 0. For 0 1 you are getting 1. For 1 0 0 1 1 1. So I already told you how to find the excitation table from truth table for SR flip flop. You apply the same, they will be getting this excitation table for D flip flop. So next one is JK flip flop. In JK flip flop, what we have done is we have taken a feedback from Q bar and we have connected to this first NAND gate, and next we have taken one feedback from Q and we have connected to this NAND gate. Okay, so this is nothing but JK flip flop using NAND gates. So you are having two inputs J and K. Here the main difference is this flip flop is also similar to SR flip flop. Only one change is here you can apply the both the inputs J and K as 1, and the condition is when J and K both are 1, if you are having 0 in the present state, you will be getting 1 in the next state. Similarly, when J and K are 1, and if you are having 1 in the next state, you will be having, sorry, if you are having 1 in the present state, you will be having 0 in the next state. Your output will toggle. Okay, this is JK flip-flop. So this is a logic symbol of JK flip-flop, and this is a diagram. Now, this is a diagram of JK flip-flop by using NOR latch. Okay, this is by using NOR latch. Now, this is a truth table of JK flip-flop, similar to the SR flip-flop. Here you are having JK. Since you are having two inputs, you are having four combinations. First combination 0 0, next combination 0 1, next combination 1 0, next combination 1 1. But the 0 0 combination can have the present state as 0 and the next state as 1. Similarly, for all inputs, we have written the present state as 0 and next state as 1. So, similar to the SR flip flop, if both the inputs are 0, whatever you are having in the present state, that will be the next state. Similarly, when J is 0 and K is 1, similarly, when J is 0 and K is 1, whatever you will be having in the present state, next state is 0. Similarly, when J is 1 and K is 0, whatever you are having in the present state, next state is 1. When both the inputs are 1, if you are having 0 in the present state, you will be having 1 in the next state. Similarly, when J and K are 1, if you are having 1 in the present state, you will be having 0 in the next state. So, this is a truth table of your JK flip-flop. I will explain once more. If J and K are 0, whatever you are having in the present state, that will be coming as a next state. Similarly, when J is 0, when J is 0 and K is 1, whatever you are having in the present state, next state will be 0. When J is 1 and K is 0, whatever you are having in the present state, you will be getting 1 in the next state. When both are 1, the next state will be the complement of present state. Now, this is a transition diagram of JK flip-flop. When you are having J equal to 0, K is equal to 0 and Q is equal to 0, it will be in the present state. Then the next state will be 0 only. When J is equal to 1 and K is equal to 1, and the present state, similarly when J is 0 and K is 1, and if it is in the and Q is 0, again the next state will be the next state will be also 0. So it will be in the present state only. Now, when J is 1 and K is 0 and Q is 0, the next state will be 1. So it will be going to the next state. Similarly, when J is 1 and K is 1 and when the present state is 0, the next state will be 1. So it will be going to the next state. Then if J is 0 and K is 0 and present state is 1, the next state is also 1. When J is 1 and K is 0 and the present state is 1, next state is also 1. Next, if J is 0, K is 1 and present state is 1, it will goes to the next state. Q is equal to 0. When J is 1 and K is 1 and when Q is 1, it will goes to Q is equal to 0. That is the state. So this is a transition diagram. Next is characteristic equation. So from the truth table of the JK flip-flop, we are drawing the KMF for Q of n plus 1. When checking the column of Q of n plus 1, wherever you are having for the corresponding inputs, you draw, you plot 1. So the input variables are J, K and Q of n. So after plotting, we are going for grouping. So This is the expression q of n plus 1 is equal to j qn bar plus k bar qn. So this is a expression for your characteristic equation. So next is excitation table, similar to that excitation of SR flip flop. So we are derived the excitation table of JK. Next one is T flip flop or toggle flip flop. So here we have connected the J and K inputs of JK flip flop and we have named it as T. So instead of in the JK flip flop, the modification what we done is we have shorted J and K and we have named it as T. So this is T flip flop. It is having only one input. Okay. So this is a circuit diagram of T flip flop or the logic diagram of T flip flop with the NOR gates. So this is a block diagram and this is how we are converting JK to T. So we have shorted J and K. Next to truth table. So we are having only one input. So it can have two combination. So 0 can have 0 can have 0 as a present state and 0 can have 1 as a present state. Similarly, 1 can have 0 as a present state and 1 can have 1 as a present state. In T flip flop, if T is 0, whatever you are having in the present state, that will be in the next state. Once again, I tell in T flip flop, if T is 0, whatever you are having in the present state, it will be the next state. If T is 1, your next state will be the complement of present state. If T is 0, whatever you are having in the present state, it is next state. If T is 1, whatever you are having in the your next state is the complement of what you are having in the present state. Next, this is a transition diagram. Then characteristic equation. By you are going for q of n plus 1, you are looking the column of q of n plus 1 and you are plotting. So this is a characteristic equation. Here we can't group because we are not having any adjacent ones. So we have grouped individually and this expression is similar to the expression of XR. So we written as T XR Qn. So next is the excitation table. Next we are going for master slave JK flip flop. So our JK flip flop is having one disadvantage. It is called race around condition. So JK flip flop is having one disadvantage. That disadvantage is called as race around condition. So if J and K are high, that is if the value of J and K are 1 and if with the width of the clock is large, there is a possibility of more than one transition. The thing is, we know that if J and K are 1, if the output is 0, it will toggle to 1. If the output is 1, it will toggle to 0. But if the width of the clock is large, there is a possibility of more than one transition. If it is 0, it will toggle to 1. Again, it will toggle to 0. So this is a disadvantage, and this disadvantage is called race around condition. So in order to overcome this disadvantage, we are going for master slave flip flop. So the master slave flip flop consists of two flip flop. One is master and other is slave. And we are having an inverter. This inverter will invert the clock to the slave. So master is a JK flip flop and slave is a SR flip flop. So when clock pulse is 1 or clock pulse is high, the master flip flop is enabled and the slave flip flop is disabled. Similarly, when clock is 0, master flip flop is disabled and the slave flip flop is enabled. When J is equal to 1 and K is equal to 0 and when clock pulse is 1, so I will show the diagram first and then I will explain.